All right, this is a tutorial on rotational inertia, rotational momentum, and velocity and torque. So we'll look at a couple of problems. This one's on rotational inertia. We're essentially going to use the equation I equals mr squared. Got 2.2 kilogram masses, 1 meter long, so the radius will be 0.5 meters. There are two masses, so we'll end up having to multiply by 2. So 0.2 kilograms times 0.5 meters, quantity squared, times 2, because there are two masses. You'll end up with 0.1 kilogram meter squared. So that would be the inertia of this particular system. Looking at a little bit different problem, we get a merry-go-round with a rotational inertia of 800 kilogram meter squared and a radius of 2 meters. A child with a mass of 40 kilogram near the edge. What is the total rotational inertia of the child about the axis of the merry-go-round? Then we're going to figure out the torque if we know the acceleration. Now remember, rotational inertia is I equals mr squared. So that's part A. And we know the rotational inertia of the child about the axis of the merry-go-round. The merry-go-round itself has this rotational inertia, but just the child is going to have a mass of 40 kilograms, 2 meter radius. We're going to square that. So then you're going to say 40 times 2 squared, or 160 kilogram meter squared. That's just the child though, so that's the child only. Now, if you've got the merry-go-round itself having an inertia, we're going to add the 800 kilogram meter squared to it for a total rotational inertia of 960 kilogram meter squared. So now, if I want to know about the torque needed for part B, the torque is equal to the rotational inertia times the acceleration. So we've got our 960 kilograms meter squared times the acceleration of 0.05 radians per second squared. And so then our torque ends up being times 0.05, 48 kilograms meters squared per second squared. And that would be that one. Now, here's a case where you've got an ice skater, rotational inertia 1.2 kilograms meters squared when her arms are extended, and 0.05 kilogram meters squared when her arms are pulled close to her body. So the rotational inertia is going to go down, she's going to spin faster. So if her initial rotational velocity was 1 revolution per second when she pulls her arms in, how much faster is she going to spin? So remember that the rotational momentum initial is going to equal the rotational momentum after or final, because momentum is conserved. So we're going to plug in and say, well, I1 velocity 1 equals inertia 2 rotational velocity 2. Well, we want that second velocity, so velocity 2 is equal to inertia 1, velocity 1 divided by inertia 2. So then we got 1.2 kilograms meters squared, velocity 1 revolution per second, divided by 0.5 kilograms meters squared. And so it should pick up speed. And be 2.4 revolutions per second. So it definitely did speed up. And so this ice skater speeds up when she pulls her arms in. Here's the last one. We've got a rotational velocity of 5 revolutions per second on a bicycle wheel. The rotational inertia of the wheel is 2 kilogram meters squared about the center. Rotational inertia of the student in the wheel about the platform is 6 kilograms meters squared. What is the initial angular momentum of the system? Then if the student flips the wheel, what's the rotational velocity of the student and the stool about their axis as the wheel is flipped? And where does the net torque come from that accelerates the student and the stool? Okay, so if we look at this problem for part A, we find that the angular momentum is equal to the inertia times the rotational velocity, which will be 2 kilogram meters squared for the wheel only, times 5 revolutions per second, which is the rotational velocity, for a total of 10 kilograms meters squared per second for the rotational momentum. And so that would be one rotational momentum. So now what would be the rotation if we flip the wheel reversing the direction of the momentum vector? What's the rotational velocity including the stool and the wheel? So now we need to use this inertia. So for B, we're just going to solve that for the velocity. So that's going to equal the momentum divided by the inertia. So it'll be 10 kilogram meters squared per second from the previous problem, divided by the inertia of 6 kilogram meter per second squared. And then what we get is 1.67 radians per second. Then part C is more conceptual, but where does the torque come from that accelerates the student and the stool? Well, it is the forces that you exert when you actually flip the wheel with your hands. So those forces of your hands acting on the wheel actually produce the torque. This has been a brief tutorial on rotational inertia, momentum, velocity, and how they all work together.